it's Emily with the Broken Science Initiative, and I'm here today to talk about different kinds of medical studies. And I'm going to highlight some of their strengths and their weaknesses and get into some of the ways that we misuse them or misinterpret them. So understanding the different kinds of studies is crucial for interpreting and applying any of the research that you're doing in medicine, as well as in all kinds of other fields. So psychology, social sciences, business, all use observational studies. Scientific studies can be broadly categorized into several types based on their purpose, design, and the nature of data collected. So in this video, I'm going to talk about observational studies exclusively. And when you read or hear news reports of an observed effect or an observational study found, this is what they're talking about. The big thing to remember, if you take one thing out of this video, it's that observational studies are corollary. They cannot say anything and they say nothing about cause. They cannot by design say anything about cause. So despite the headlines that you see, there is no cause in observational studies. So one example of this that people don't know is that things like cigarette smoking causes lung cancer was an observational study. That was all an association, but it was believed causal because the link between smoking and lung cancer was enormous. It was like 10 to 20 times higher. And we can't quite imagine or explain how such a powerful association came from any other combination of confounding variables or biases. So we've kind of just accepted it to be true, despite it being an observation and therefore not proof of any cause. So a good tip off when you're reading the news and you see headlines like coffee consumption was associated with blah, or living close to power lines was linked to blah. Those are observational studies. So you need to be aware they're associated, and links are words that are sort of clues where we should know that they are going to say absolutely nothing about cause. And if they claim to, they're wrong. So observational studies are studies where researchers observe and measure variables. The main strength of observational studies is that they are useful in identifying associations and generating hypotheses, especially when experimental studies are not ethical or feasible because they're too expensive. We cannot establish anything causal, and there is a potential for confounding variables and biases. You need to read these carefully. So a confounding variable is just an outside influence that can change the effect of a dependent or an independent variable. What does that mean? Well, it's basically any outside influence that has some exposure that causes an impact on someone's health. And many of these are actually unknown to the researchers, so it's really impossible to measure their influence on risk. So an example of this is like if you're studying cardiac health and tea drinking, we might find that people who drink a lot of green tea have a reduced risk of cardiac events. But these tea drinkers may also be doing CrossFit. They may also eat a naturally occurring diet. They may meditate. So they're generally healthier than the non-tea drinkers. So those are the confounding variables that make any claim of cause impossible in an observational study. One kind of observational study is called case studies. And these are basically detailed investigations of a single individual or a single group or a single event. They can provide really valuable insights and again, help to generate a hypothesis, but they cannot establish anything causal because they involve only a single case. And it would be impossible to make any other bigger claims or rule out any other potential causes. And they're really just limited because it's just this one sample. So an example of this would be a case study might investigate a patient who developed a rare side effect after taking some new medication. The study can then generate a hypothesis about that potential side effect of the medication, but it cannot prove causation. And because there may be so many other factors, it becomes really tricky when people try to claim cause in a study like that. So the next observational study that I'm going to talk about is called a cross-sectional study. Now, this just really provides a snapshot of a population at a very specific time. They can identify associations between variables, but again, here you go, they cannot say anything about cause or any kind of temporal relationship, which means over time, because they don't track changes over time or account for other potential confounding variables. So an example of a cross-sectional study might be considering the consumption of diet soda. And they might find that there's an associated higher risk of obesity for the people who drink more diet soda. But again, this is limited because perhaps the people who are obese that they're studying consume more diet soda because they're trying to lose weight. So this is often referred to as reverse causality. It isn't that the diet soda makes people fatter, but that people who struggle with their weight are more likely to drink soda. So when they're measuring those two things, they're finding there's a relationship, but it may not be the one that they're purporting it to be. Another kind of observational study is called a cohort study or prospective studies, and these involve tracking a group of people over time. Now, these can establish a temporal relationship because they're tracking people over time, and often they try to look at causality, but they still have some really serious limitations. These kinds of observational studies can introduce what is known as measurement error. An example of this would be many nutritional studies are prospective studies, and they might do something like send out a food frequency questionnaire or some other kind of questionnaire, and they ask people to recall what they ate. But people may not measure their food intake properly or measure it the same. Or in some cases, surveys are so poorly designed, like one that was on colorectal cancer, one of my favorites, that asked subjects to measure how many cups of ribs they ate in a month. Now, how do you do that? How do you measure a cup of ribs? Are the bone in, bone out? Not to mention that people don't really accurately remember what they ate, nor do they remember how much they ate. So those kinds of recall questionnaires are highly problematic. Prospective and cohort studies also have another potential big problem, which is called a lost follow-up. A cohort study might involve tracking people over a group of time, so let's say over several years, and they want to see how different factors have affected their health. However, over time, some participants might move, change their contact information, or just generally decide to drop out of the study because they don't want to do it anymore, which makes it difficult or maybe even impossible for researchers to collect accurate data on the entire sample set. So this loss to follow-up can introduce all kinds of bias into the study results because the people who drop out of the study might be systematically different from those who remain in the study. And it can also reduce the statistical power of the study because it's reducing the number of subjects by a certain amount. So, like all other observational studies, cohort studies, even though they can adjust for some of the known confounding variables, which the other ones can't necessarily do, there are still really big unknown confounding variables that are not accounted for because they're not known. Okay, let's move on to case-controlled studies, which is a kind of observational study that compares individuals with a very specific condition to individuals without that condition. They can identify association between exposure and outcome, but again, they cannot establish anything about causation or a temporal relationship because they're retrospective. And there's a huge potential for recall bias, as we discussed earlier, and selection bias. A case-controlled study might find that people with lung cancer are more likely to have a history of smoking compared to people without lung cancer. But let's think about this. This does not prove causation, in part because there's a recall bias, as somebody who has lung cancer might be more likely to remember and report their smoking history compared to somebody who doesn't want to remember that they smoked or doesn't, really even think they smoked that much or has no accuracy around their recall. So there might be other confounding variables in something like that too, in terms of exposure to air pollutions, genetic predispositions. All of that will contribute to your risk for lung cancer. So those are the most common observational studies. And it's crucial to consider all of these limitations with each of the scientific studies that I mentioned, each of those subcategories, and think about it a little bit when you're reading the headlines or you're reading a medical journal study. Because I think these are really important for understanding association and for generating a hypothesis, but their limitations really limit them. So the confounding variables, the bias, the inability to establish a temporal relationship with much reliability over time are all factors that we need to consider. So when you read a story in the news about an observational study, or your doctor tells you of some observed response in something that they've seen or they know about, remember that this is not definitive in any way. It's suggestive and it's an interesting idea, and it should probably be followed up on. But unless it's actually been tested in an experiment, in a rigorous trial, independently and replicated, which maybe is a lot to ask for, but it's not worth as much as people want to make it out to be. And certainly in the news business, people see observational studies and oftentimes they make big claims and they're exciting headlines and they're things that they know people will read. So they push it out to the public, taking it even a step farther than the scientists might by using language to make it sound like it's causal when it's not. So remember, you want to keep in mind this idea of sort of association and link, like big X through the idea that there's any causal claim being made. It's impossible. They cannot make a causal claim. Okay, that's observational studies.